So I want to find the region, rotate the region enclosed by y equals x and y equals x squared about the x-axis as letter A. And then I want to go about a line y equals 2. And that's new for us. So we're going to start by reviewing how to rotate these curves about the x-axis. Guys, I picked these curves because, again, I think they're easy. I think you think they're easy too. There's the parabola of the line. We can see that little region there in green. And we're going to spin that region about the x-axis.
So we make it like a cone? Is that what we're doing for this issue?
Exactly. It's gonna be kind of like a cone. So when I take a picture here, do you guys see an inner circle and an outer circle? So the cross-sectional area of this is a washer. Okay? So we're going to have a washer here. Because if I want to find volume...
Wait, why? I don't get that.
All right. So take your butter knife, and I'll do it here in purple. Take your butter knife. Can you cut it right here? And you think about that spinning around. When we rotate it, you have to see that it's going to be that. There's going to be a hole here in the middle.
Oh, like right where it doesn't hit the
Yeah,
x-axis.
where there's no region, and then it has an outside radius here.
So the hole's where you cut it.
The hole's where we cut it. Now, which function is going to be the cutter this time? The inside hole is cut by y equals x squared. What's the outside hole made by? Y equals x. Now, I'm going to grab a book print off of all this because, again, I don't think I do justice. Let's blow this in. It is hard for me to draw these situations. So everybody, there's the situation. Here's my region in green we had, right? Between 0 and 1. And everybody, it shows the washer here in red. Do you see it? And again, I'll get my right.
It is easier to see when it's not touching the x-axis partially.
Yep. And we're going to work from there. Now, listen, we're going to draw that, and we're going to look at this circle here, all right? Instead of looking at it kind of isometrically, I'm actually going to redraw it from a plane view, right? We're going to look dead on. We're going to look down the x-axis at it, okay? Every single time. We're going to always draw that cross-sectional area shape. And it's not always a circle. It's not always a washer. It can be rectangles. It can be triangles. That's when it gets more interesting, a little more fun, okay? Not so boring. All right, so we come back to this. We know that's the situation in the upper right. I'm going to spin this about the x-axis. So I picture this happening, and I can picture, when I take my butter knife cut, I'm going to get this red washer. And I always label it the same. Textbooks do it different, but I have an outer radius, right? And I have a inner radius. And I do not get cute worrying about what they are right away. Personally, I always start these problems the same way. I say, hey, I know the volume is the integral from A to B of the cross-sectional area, which is this washer, guys. This is the cross-sectional area. If I take and get one slice, times dx. The dx is the thickness of it, right? But it's also what we use to do the integration. I know it goes 0 to 1 because there were easy intercepts on this problem. That's why we picked these two functions, right? And I don't get cute. I don't try to substitute for x right now. I say, hey, look at this red shape. Put your Algebra 1 hat on. What's the cross-sectional area? Pi RO squared minus pi RI squared dx. Now, obviously, we can't integrate RO and RI with respect to x. We always, everybody, take that pi out of there. That's why one of the rules we learned right away. And now I'm going to deal with what is the RO. All right?
How'd you pick the 0 and 1?
That's RO is our outside, RI is our inside.
Zeros and I's.
Yep, it's a outside and inside, okay? So we know the radiuses. Now, I'm going to try to do this. Let's see if I'm going to get rid of the green. And I'm going to try to blow up my graph. And I'm going to erase a whole bunch of stuff here. So we have enough room. I'm going to erase all this stuff so we can make it quite a bit bigger. And hopefully have room to do it. All right, here we go. Let's see if this actually works like I hoped it does. Oh, not horrible. All right, there it is. You have to see, you guys see that this is RO, right? And it's Y high, guys. This height is Y to that black line, right? It is Y tall right here. Okay? But what Y is it? That goes to the black line, which was Y equals X. So R over here is equal to X. What is the bottom line? The bottom line down here, any RI at any point, goes to the blue line. It is the Y height to the blue line. What's the blue line? The blue line was Y equals X squared. So what is RI? RI is X squared. Now we just are substituting in. So I have RO, which is X squared, minus RI, which is X squared squared. All right? And now this problem, if I say evaluate or write the limit but do not evaluate, or write the integral but do not evaluate, you would stop right here. If I said write the integral and evaluate and integrate the function here, we would integrate this. So the next step is integration, right? We should all see at this point, add 1 to the powers, right? Divide by the new coefficient from 0 to 1. Now to evaluate, I just have to...
Wait, you told me that was a O and an I.
Yep.
So why'd you just say 0 and 1?
Oh. All right. Right here, these are 0 and 1.
Yeah, why'd you pick that? So I want to...
Oh, okay. We picked 0 and 1. All right. This is an O. This is an I. That's what all right?
I wrote them all wrong in here now.
Oh, you'll be okay. Calista, look back up at the original function up here.
Yeah.
Where does the intersection start? At x equals 0. Where's the curves intersect again? X equals 1.
Oh, okay.
Those are the limits of integration. All right? So now, the last step. We get pi, x cubed, well, not x cubed, what am I doing? I gotta put numbers in. I like 1. This is why we pick these problems, because it makes really easy math. I always show the zeros. So I get 5/15 minus 3/15. I get 2/15 pi when I do the math there. And that is the volume of the region between those two curves rotated about the x-axis, the exact volume. And if I go to 100%, so you can see the whole page, again, I can't, or the entire page, I can't stress enough how much space this takes every single time. Usually I put one of these on a page when I'm giving tests. So tests often are, 9 pages long. It's just a lot of white. That we have done before, all right? That is a shape, all right? And that is the volume about the x-axis. Put that up there with the x-axis stuff. Now the question becomes, let's rotate the same exact region, but not about x-axis, but about x equals, or y equals 2. So we have that small region, all right, down in the corner. And I'm just going to make the region. It goes from 0 to 1 still. You guys agree? Looks kind of like a banana. At least that's what I see. I see a little banana shape here, right? But instead of spinning it the way it's shown up here on this figure up here, all right, to make that kind of cone shape with that washer ring, they say, hey, rotate it about the line y equals 2. So now this is going to spin this way around. We spun, at letter A, we spun about the x-axis. Now I'm doing letter B, which says spin that, I want to spin that about the line y equals 2. Well, this takes a little vision again, so I have the shape from the book. That's why we're working from here. better window in some bigness here so we can see this. We have the same region. This region up here, okay, that's the region. But now instead of spinning about the x-axis like we did up here, we're going to spin it up around y equals 2. So that region is shown, and this is much harder to see, but there's that region. And they are spinning that about the y equals 2. And you see there's a void here. Do you guys see it? And then it is filled here at the top. It's going to be another washer, obviously. All right? But this is going to be a much more difficult RO and RI, our outside and our inside. They're much different. They're not just the function value anymore. So our picture is going to be critically important about what we do here. All right? And when we do that, we're going to have to figure out what those are. So we're going to spin the region. And it's still the limits of...
Is the outer one the x squared?
Nope, not this time.
Oh,
yes it is. Yes it is. But it's not going to be y equals x squared. It's not going to be x squared. It's the x squared function is going to have an RO. But here's the thing I want you to realize right now, Callista. Here's the RO, right? Like you said, to the x squared, that green arrow.
Yeah.
Guys, think about that. We have to define that as a height. But we're finding it from the center, y equals 2. I don't know that. What I know is that it's y tall from the x-axis. All right, this is going to be a little bit complicated. So we're going to make the ring, and then we're going to work our way to there, okay? We're going to come back to that thought in a second, Callista. You guys agree it's a washer. When we look at the cross-sectional area, this problem is going to have a washer cross-sectional area. So our AX, our cross-sectional area, is RO, which goes to the x squared function, but it's not x squared, and RI. All right? And so this much doesn't change. Volume goes. We'll go right to the limits of integration, 0 to 1, right? It's going to be dx. It's going to be pi RO squared minus pi RI squared dx. All right? But now the problem is we have to define RO and RI. All right? And if I bring y equals 2 a little closer, all right, get it out of scale a little bit, and I think about getting rid of that little red so we can see in there. If I go to the outside radius, it is what we talked about here. It goes from here to here, right? That is RO. But guys, we don't know what that is. I'll just write that this is RO, right? That's RO for distance. But we don't know. We don't know how to write that. That's just RO. All right. I'm with Callista. How tall is it from the x-axis to the function? X squared. It's y equals x squared. It's y high and y is equal to x squared this time.
So it's 2 minus x squared.
Boom! You see it. Everybody, and you went right to the answer. I'm going to show them the other way. You guys see RO plus y has to be 2? RO plus y has to be 2. So what's RO? RO is 2 minus y. But what is y? In this case, y is x squared. So RO is 2 minus x squared, okay? Bingo. Now, there are some rules here. You're going to see a pattern emerge. I don't teach the pattern. A lot of college professors do. All right? So I put that aside. All right? And I say in a different color, we haven't used red yet. Here. You guys agree RI here is this one?
2 minus x.
It is. And this is y equals x. And RI plus y is 2. But y is x. So I just changed the y to an x because they're equivalent. All right? And if I do this, boom, 100%, I now have RI and RO. So let's go down to my function. Whoop, here we go. The sound of us being successful. How about RO squared? What's RO? RO is 2 minus x squared. What's RI? 2 minus x squared dx. Now you have two choices. You can either do a u substitution, all right, which is ugly, right? Or how about we just do a little bit of algebra 1 and square some binomials? All right? Albany likes this. They like squaring out things. It's not like this is 2 minus x squared to the 7th power, right? Though you can get the right answer doing it that way. Do we all agree it's 4 minus 4x squared plus x to the 4th for the first one? Oh, wait a second. What am I doing? This should be a minus, right, guys? Screwed up. All right? Minus. Oh, my goodness. Well, I might square this binomial out this way. 4 minus 4x plus x squared. But then you have to do what? Distribute the negative. And I like having smart boards because I can do it this way then. Minus, plus, minus, plus, minus. And on paper, maybe you have to write one more step. But before now I combine anything, what can I do? I got some like terms. Let's do some order of operations, some descending power. If you need to, have a freshman sit with you. X to the 4th. Negative 4x squared, negative, I think it's negative 5x squared. And it's plus 4x. And 4 minus 4, right? Does that take care of all my terms? Yeah, I think so, right? And I don't want to make a math mistake here. It's really easy to. And then I go dx. Now, gut reaction, should this be more than 2/15 pi? Should be more in the last answer, don't you guys agree? There's a lot more stuff happening around, so let's see if that happens. Let's evaluate it. I think it's x to the 5th over 5 minus 5x cubed over 3. And I know some of you are going to scoff when I write that, but I do not think I just integrate 0 to 1. All right? And so now we grind this out. I get 1/5 minus 5/3 plus 2 minus 0 minus 0 plus 0. I write it out every time so I don't forget it. I know when I put zeros into all those x's, there's 0. 1/5 minus 5/3. Well, minus 5/3 plus 2, guys, is a positive third, right? And a third plus a fifth is 8/15. So the answer to this is 8/15 pi. And if you guys want to get good at math like that, it's just practice. Become a math teacher. All right? I'll trust that you can do that in your calculators. Everybody. Entire page. That volume was 4 times bigger. And no, you don't just double the 2, Anthony, okay? You can't, there is no tricks here, okay? The only tricks you get is what you put in your breakfast cereal in the morning, right? Here we go. You can't just look for paths here. None of that system stuff works, all right? But that's the thing. And everybody, I think the key to all these problems, without a doubt, is right up here. It's knowing that volume equals the cross-sectional area dx. It is making what I would call a tremendous picture of your cross-sectional area and then tying that to a graph. And with that, we'll keep practicing.